Turbulent pipe flow. For turbulent pipe flow, we need not solve a differential equation, but instead proceed with the logarithmic law as described before. The correlation is for UR, for example, in a pipe flow as a velocity function on U star equals to the relation K is a 1.41 ln U star nu plus B, where shown in this picture B equals to 5 from previous and K equals to 0.41. So now we can replace pi with our variables, in this case r minus r. Now we can calculate the integration for calculating velocity. First we should calculate Q. Q is equals from integration V dA. We have a relation for U as V plus BR 2PR dr. And V equals to the Q on A. A is PR2 multiply the integration of U star on K ln R minus R on nu plus B 2PR dr. So V is obtained this relation. Introducing K and B before, we have from before 5. Now we can calculate the V on U star, for example. On or a function of friction factor. Moreover, the argument of the logarithmic in the equation for V here, we can also have the relation of for Reynolds for the U star. Nu is viscosity U star which is equal to the function of Reynolds D and the friction factor. Introducing these two relations, we can obtain a final relation for friction factor. With eliminating u start from the relation, final relation is minus. So we can write again a relation for the friction factor and Reynolds number of the flow. Again, in other words, by simply computing the mean velocity from the logarithmic law correlation, we obtain a relation between the friction factor and Reynolds number for turbulent flow pipe flow. For turbulent pipe flow. Prandtl derived another equation and adjusted the constant slightly to fit friction data better. So we can write Prandtl relation. Prandtl relation for the turbulent pipe flow is have a modification on constant logarithmic of this is the accepted formula for a smooth wall pipe. Smooth we can calculate various quantities for friction factor with the various Reynolds numbers. Thus, F drops by only a factor of 5 over a, for example, 10,004. Let me write here for various Reynolds number, we have a drop in the friction factor. For example, at Reynolds equals to the 4,000, we have friction factor from Prandtl equation is, and for Reynolds, for example, 10 over 8, we have a friction factor there. In this case, we can see that the change from Reynolds 4,000 to 10 power 8, the Reynolds friction factor we decreased 1/5. Anyway, this equation equation of the Prandtl is cumbersome to solve if Reynolds number is known and F is wanted. There are mainly alternative approximations in the literature from which friction factor can be computed explicitly from Reynolds number. Another relation for the friction factor in turbulent pipe flow is a conditional function with Reynolds between Viscous H dot Viscous and for from another reference line in the reference our reference in black and white 7th edition. Let's use a student of Prandtl. We have also some relation for the heat loss during a heat loss from in a pipe, turbulent pipe flow regime, which is heat loss as before we had on rho g, which was equals to this relation V2 on 2G. Mu on rho VD L on D where delta P is equals to for a pipe flow, turbulent flow pipe at low turbulent Reynolds number. This explains why hydrogen delta for pressure drop begin to increase as 175 power of the velocity. Note that delta P varies only slightly with viscosity. Let me write delta P varies with viscosity, which is characteristic of turbulent flow. Introducing the Q equals to area multiplied to the velocity into the equation before we can obtain the relation for delta P equals to the a function of volume of fluid L, the density of mu D and Q. This is a pressure drop in a pipe related to viscosity, geometrical and fluid specification. For a given flow rate Q, the turbulent pressure drop decreases with diameter even more sharply than the laminar formula. Thus, the quickest way to reduce required pumping pressure is to increase the pipe size, although of course the larger pipe is more expensive. Doubling the pipe size, decreasing pressure drop by a factor of 27 for a given volume of flow. With comparison between the equation of the pressure drop in the turbulent flow in a pipe with the, for example, our previous relation with the overlap of turbulence and laminar flow relation, which was U max. Let me write on U star plus B. Combining the equation, we obtain the formula relating mean velocity maximum is the Peter. Combining this relation and friction factor, we can obtain a relation between the friction factor and velocity on the ratio of velocity and the maximum of the velocity. The ratio varies Reynolds number and is much larger than mean. We can obtain various ratio of velocity on the maximum of the velocity and Reynolds. We are going to explain the effect of Waldorf. It was not known until experiment that surface roughness has an effect on friction resistance also. So let the effect of roof wall. It turns out that the effect is negligible for laminar pipe flow, and all the laminar formulas derived in this section are valid for roof wall also. But turbulent flow is strongly affected. So for laminar flow, the equation before is valid for roof wall and for turbulent flow is strongly affected by roughness consider this picture. The linear viscous sublayer extends. In this picture, the linear viscous sublayer extends out only to y plus equals to the and compare it with the diameter, the sublayer thickness by S on D equals to the for example, at Reynolds you can calculate F equals to at Reynolds and now friction factor and also a wall roughness of about will break up the soil layer and profoundly change the wall law in the pipe turbulent flow. Measurement of the velocity function in turbulent roughness wall from flow by Prandtl student shown that a roughness height epsilon will force the logarithm law profile outward on the abscissa by an amount approximately equals to the ln epsilon plus, where epsilon plus is the wall epsilon on the flow properties. The slope of the logarithm law remains the same. But the shift outward causes the constant P to be less by an amount of Ln epsilon. There are values studied on simulating roughness by gluing uniform sand grain onto the inner wall of the pipe. They measured the pressure drop and flow rates and correlated friction factor versus Reynolds number as shown in the picture B. We see that laminar friction is unaffected by turbulent friction. After an onset point, increase monotonically with the roughness ratio epsilon on D. So for laminar flow on friction is unaffected. Part turbulence flow increase monotonically with the roughness ratio is a relation for the roughness height on the diameter of the duct. For any given epsilon on D, the friction factor becomes constant at high Reynolds numbers. These points of change are certain value of epsilon on epsilon u star on mu. So we have various conditions for the coefficient. If the coefficient of epsilon studied in practice is epsilon plus is smaller than hydraulically smooth wall, epsilon and transitional roughness and for epsilon greater than fully roof wall. Roof wall flow sublayer totally broken off and friction independent of Reynolds number. In this case, friction is independent of Reynolds number. For fully roof wall, we had this condition. The log law downshift delta B for this relation is, as we said before, and the logarithmic law, that means log law and logarithm law for fully roof wall. We have this relation and we have the relation for log law relation delta B. And we have also for full and the logarithm law we have u plus b minus delta b, which E equals to this relation. The viscosity vanishes and hence fully roof flow is independent of Reynolds number. If we integrate this equation to obtain average velocity in the part, we can obtain this relation. Or we can write for friction factor, we have this relation F for F minus 2 there is no Reynolds number effect. Here the head loss varies exactly as the square of the velocity in the case. So we can write Q2. The friction factor increases by 9 times as the roughness increases by a factor of 500, 5000. If we calculate the various friction factor, we can cite this result. In the transitional roughness region, sand grains behave somewhat differently from the commercially rough part.